When you picture Earth, I mean, what jumps out? It's the
Uh,
blue, right? The
right.
water.
Absolutely. Oceans, rivers, clouds, it's everywhere.
It's in us. It carves canyons. It falls from the sky. I mean, it's so incredibly common.
Yeah.
We take it for granted. We rarely stop and think about what it is, chemically speaking, just ordinary stuff.
But see, that's the twist. Scientifically speaking, water, good old H0, it's probably the most extraordinary material there is. It behaves in ways that, well, frankly, defy the rules that other liquids follow.
And that's the core paradox we're really going to dig into today, isn't it? We've got some great sources here, lots of hands-on science stuff, actually, looking at the fundamental structure of water.
Yeah, the mission today is sort of peeling back the layers on that simple H0 label. We want to show you the unique, sometimes really weird, but absolutely vital differences that make water so special.
So the big question, how does this seemingly simple molecule, just three atoms, end up shaping landscapes, driving weather, and basically underpinning all life?
It's all hidden in the structure. Let's dive in, maybe starting right at the molecular level.
Perfect. Let's unpack the architecture. Two hydrogen atoms, one oxygen atom. Sounds simple, maybe even symmetrical. But the way they're put together, that changes everything.
Exactly. The arrangement is absolutely key. HO isn't a straight line, like HOH. No, it's a bent molecule. The hydrogens are attached to the oxygen at an angle, about 104.5 degrees,
Just a slight bend. Why does that little angle make such a huge difference?
because it creates an electrical imbalance across the molecule. Oxygen, see, it's very greedy for electrons. It pulls them strongly towards itself.
Okay.
So that makes the oxygen end of the molecule partially negative, and it leaves the two hydrogen atoms kind of exposed, partially positive.
Ah, right. So the positive and negative charges don't cancel out neatly in the middle. The whole molecule ends up with a positive side and a negative side, like a tiny magnet.
Precisely. And that's what we mean by a polar molecule. That persistent charge difference is its superpower.
And this isn't just theory, right? Your sources mention an experiment.
Oh yeah, a classic one.
Yeah.
You can actually see this polarity in action. Just get a thin stream of water falling, say, from a tap. Then take something like a plastic comb, rub it on your hair or wool to give it a static charge,
Okay.
and bring it close to the stream of water.
And the water bends towards the comb, even without touching it.
It does. The charged comb attracts the oppositely charged part of the water molecules. Even with gravity pulling the water down, that tiny molecular electrical force is strong enough to pull the whole stream sideways. It's really cool to see.
Wow. So that inherent stickiness, that polarity, is that why water is such a good solvent? The universal solvent, they call it sometimes.
That's a huge part of it, yes. When you put a polar substance like salt, sodium chloride into water, the water molecules swarm around the ions.
How does that work?
Well, the negative oxygen ends of the water molecules surround the positive sodium ions, and the positive hydrogen ends cluster around the negative chloride ions. They form this sort of protective cushion or envelope around each ion.
Keeping them separated.
Exactly. It keeps them separated and suspended in the water, allowing them to move around freely. That's what dissolving is, and that's how water picks up minerals from rocks and soil as it flows.
Okay, so polarity is huge. And it connects to another really unique thing about water. It's the only common substance we find naturally in all three states on Earth, right? Solid ice, liquid water, gaseous vapor.
Correct. But it's the solid state, ice, where things get really weird, scientifically speaking.
You mean the fact that ice floats? Because usually solids are denser than their liquids, they sink.
Precisely. It's water's great density puzzle. Most liquids, as you cool them, they just shrink and shrink, getting denser and denser, right up until they freeze solid.
But water doesn't do that.
Well, it does,
Hmm.
but only up to a point. Water contracts and gets denser as it cools, but only down to 4 degrees Celsius. That's about 39 Fahrenheit.
Okay, 4 degrees C, what happens then?
Below 4 degrees C, it stops shrinking. It actually starts to expand. The molecules start pushing each other slightly farther apart as it gets colder, and it keeps expanding until it freezes solid at 0 degrees C.
That's completely counterintuitive. Why? What makes it expand when it should be contracting?
It goes back to those hydrogen bonds.
Exactly.
The attraction between the positive hydrogen of one molecule and the negative oxygen of another. As the molecules slow down below 4 degrees C, these bonds become more stable and start locking the H0 molecules into a very specific, open, hexagonal crystal structure.
Like a honeycomb.
Kind of like a microscopic honeycomb, yeah. It's a rigid lattice. And because it's so open, this structure forces the molecules to be farther apart, on average, than they were bouncing around in the liquid state.
So the ice ends up taking more space. The sources say about 10% more volume.
Roughly, yes. About 9 or 10% more volume than the liquid water it formed from. And if you have more volume for the same mass, that means it's less dense.
And that's why ice floats.
Wow. Okay, let's unpack the implications because this is huge. What does that 10% expansion mean in the real world?
Well, geologically, it's a massive force. Water seeps into cracks in rocks, then freezes, expands.
Breaks the rock apart. Frost weathering.
Exactly. It's a major driver of erosion, shaping mountains and landscapes over millions of years. That 10% expansion packs a real punch.
And biologically,
Oh, biologically, it's everything. If ice were denser than water and sank, think about what would happen in winter. Lakes, rivers, even oceans and cold regions would freeze from the bottom up.
and eventually freeze solid, killing almost everything living in them.
Pretty much. Life as we know it in aquatic environments wouldn't be possible. But because ice floats, it forms an insulating layer on top, protecting the liquid water underneath from the cold air. It keeps the deeper water liquid, allowing fish and other organisms to survive the winter.
It's actually amazing that one weird property, that expansion below 4 degrees, makes life possible. But it also has, well, downsides, right? Like icebergs. Absolutely. The Titanic is the classic tragic example. That floating ice, the same phenomenon that protects lake fish, means most of an iceberg's mass is hidden underwater, making it a huge hazard for ships. That visible tip is just a fraction of the danger.
Okay, let's shift focus a bit. From density to the surface of water. Why does water form those perfect little beads on, say, a freshly waxed car? Or why are raindrops roughly spherical?
That's all down to something called surface tension. It's like water has this invisible elastic skin stretched across its surface.
An elastic skin, how does that is it the hydrogen bonds again?
It is, combined with the polarity. Think about a molecule deep inside the water. It's being pulled equally in all directions by the molecules surrounding it, right?
Okay, yeah, balanced forces.
But a molecule right at the surface doesn't have any water molecules above it pulling upwards. It only gets pulled sideways and downwards by its neighbor.
So the forces aren't balanced anymore?
Exactly. Those inward and sideways pulls become stronger, pulling the surface molecules closer together and resisting anything that tries to stretch or break that surface. It creates this cohesive film.
And because water's polarity and hydrogen bonding are so strong?
It has an exceptionally high surface tension, actually the highest of any common compound liquid at room temperature, according to the sources.
And you can see this, right? Like the experiment where you carefully add drops of water onto a penny.
Yeah. You can stack up way more drops than you'd expect. The water forms this big, bulging dome because that skin, the surface tension, is holding it all together, stretching, until finally gravity wins and it spills.
So that's water molecules sticking strongly to each other. That's cohesion. But there's another force at play too, right? Adhesion.
Right. Cohesion is water-to-water attraction. Adhesion is water attracting to other surfaces, like glass or paper or plant fibers, and there's often a tug of war between these two.
And when adhesion wins, what happens then?
When adhesion is stronger than cohesion and the water's weight, you get capillary action. Water seems to defy gravity and climb upwards into narrow spaces.
Like sucking water up a paper towel.
Exactly. Or, much more importantly, how water climbs up the incredibly thin xylem tubes inside plants and trees, from the roots all the way to the leaves.
So plants don't need a pump, like our heart. They rely on adhesion pulling the water up these tiny tubes.
Largely, yes. Adhesion pulls the water up the walls, and cohesion makes the water columns stick together. It's this amazing physical process that allows giant trees to get water hundreds of feet high without any mechanical pump. It's mind-boggling physics.
Wow. And we can mess with this surface tension, can't we, with soap?
We sure can. Soaps and detergents are specifically designed to disrupt it. They have molecules with two ends. One end is polar, loves water, and the other end is nonpolar, loves grease and oil. The polar end pushes its way between the water molecules at the surface, breaking up those strong, cohesive forces. This reduces the surface tension, makes the water wetter, in a sense, allowing it to spread out, penetrate fabrics, surround dirt particles, and wash them away.
Okay, we've covered the physical side, the polarity, density, surface tension. Let's pivot to water's role in chemistry. Now, water itself is super stable, right? It takes a lot of energy to break H2O apart.
Oh, incredibly stable. You need something like electrolysis, passing a strong electric current through it to force it to split into hydrogen and oxygen gas. On its own, it holds together very tightly.
Yet, paradoxically, it seems essential for almost all chemical reactions, especially in biology. How does it act as a catalyst if it's so stable itself?
It mainly acts as the essential medium. It enables reactions rather than directly participating in breaking its own bonds. Think about baking, like the sources mentioned, mixing baking soda and cream of tartar.
Two dry powders,
Yep,
nothing happens.
right. They could sit there forever, but add water.
And fizz. Carbon dioxide is released.
Exactly. What the water does is dissolve both solids. Remember that solvent property. It surrounds the ions from the baking soda and the cream of tartar with those little water envelopes.
Ah, so it frees them up to move around.
Precisely. Once dissolved and mobile, the ions can actually bump into each other, collide, and react chemically to produce the carbon dioxide gas that makes your cake rise. The water provides the meeting place and the freedom of movement for the reaction to happen.
That makes sense. And this chemical role brings us to maybe the most fundamental measure of water chemistry.
pH.
Right, the power of hydrogen, which sounds simple, but the scale itself is really important to grasp. It measures the concentration of hydrogen ions, H plus R, telling us if a solution is acidic, neutral, or basic.
Below 7 is acidic, 7 is neutral, above 7 is basic, pure water is 7.
Correct. But the key insight here, the thing people often forget, is that the pH scale is logarithmic.
Okay, logarithmic. What does that mean practically? It means each whole number step represents a tenfold change in acidity or basicity. So if you go from pH 7 down to pH 6, the solution is 10 times more acidic. Go down to pH 5, it's 100 times more acidic than neutral water.
Wow. Okay, so a small change in the number means a huge change in the actual chemistry.
A massive change. If you shift from, say, pH 8 to pH 9, it's become 10 times less acidic or 10 times more basic. This huge jump for each unit shows just how potent those hydrogen H+ and hydroxide OH ions are, even in tiny concentrations.
And that explains why things like acid rain, which might only shift the pH of a lake by 1 or 2 points, can be so devastating for fish and other organisms that need a very specific, narrow pH range to survive.
Absolutely. They just can't cope with a 10-fold or 100-fold change in their environment's acidity.
And the sources mentioned a cool home experiment for this too.
Yeah, using red cabbage juice. If you boil red cabbage, the purple juice acts as a natural pH indicator. It turns reddish or pink in acids like vinegar or lemon juice, and blue or even greenish yellow in bases like baking soda solution. A very visual way to see pH in action.
So, wrapping this up, we started out thinking water is just common, ordinary, but this deep dive really shows it's anything but. It's uniquely extraordinary.
It really is. And it all seems to trace back to that simple bent H-O structure and the resulting polarity.
Yeah, that polarity drives its solvent power, the weird way its density changes when it freezes, allowing ice to float, its incredibly high surface tension, the cohesion and adhesion driving capillary action.
And its role as the essential stage for countless chemical reactions regulated by that powerful logarithmic pH scale. It's all interconnected.
And there's one more connection we can make, bringing us back to water as a solvent. We mentioned pure distilled water doesn't really conduct electricity well. It needs dissolved stuff, ions, to carry the current.
Right. Pure HO isn't conductive. So a final thought for you, the listener, to maybe explore. The sources suggest a simple test. Set up a basic circuit with a battery and a small bulb, and dip the wires into a glass of your own tap water. Does the bulb light up? Does it conduct electricity?
Assuming it does, which most tap water will.
Then the question becomes, what is dissolved in your local water that's allowing that current to flow? What specific ions, minerals from the ground, stuff from the pipes, maybe chlorine from treatment? What is it in your water that's carrying that charge?
It's a great way to connect all these ideas, structure, polarity, solvency, right back to the water coming out of your own faucet, a little kitchen science investigation.
Exactly. A reminder of the hidden complexities in the everyday.
Fantastic stuff. Thanks for walking us through the science of HO.
My pleasure. It's a endlessly fascinating topic.
Thank you for joining us on the deep dive.
We'll catch you next time.